We have Shravan here, who is an incoming faculty at UT Austin. He's joining me in the great state of Texas, where it's warm and humid and fun. Less so for him than for me, but you know. All right, with that, go ahead, Shravan.
Hopefully it actually works. Fingers crossed.
Oh.
It's blinking.
Blinking.
I can get the power adapter if that helps. Oh, okay. Display settings. All right, get rid of. How do I get rid of presenter view? Oh, yes, sweet. All right, hello everyone, I'm Shravan, and today I'm going to be telling you about HFI, which is a hardware extension to help with the in-process isolation of code. So this is actually joint work with a bunch of folks across academia and industry, and the details are on slide. So let me start today by telling you hopefully something that is fairly obvious, which is page table-based protection schemes are bad at isolating small things. So the primitives I'm talking about here are things like VMs and containers and processes, which are totally great for what they do, but when you isolate small snippets of code, functions, libraries, and so on, they tend not to work as well. And this sometimes limits how we build applications. So for example, applications today typically are monoliths. You can't just pick up hardware and say, isolate this library. And this actually makes the security of applications rather fragile. And the same limitations of hardware also affect clouds. Clouds can't do, and edge platforms, for example, can't do fine-grained isolation. They have to rely on techniques like VMs and containers where there is a large amount of overhead. There's context switch overheads, startup time costs, resource footprints that make things expensive. So what the trend we are seeing recently is that more and more these applications and these systems are turning to software-based fault isolation for in-process sandboxing. The idea being that spinning up a new instance or context switches are dirt cheap in this sort of setup. And if we have a whole bunch of companies relying on it. And this sort of software-based fault isolation, more or less, is powered by WebAssembly today. So if you're not familiar with WebAssembly is a platform-independent bytecode, and it's designed for isolation. And for today's talk, it's sufficient to think of WebAssembly as this compiler that produces a sandbox binary. So a concrete example, I'm going to take the sources of libjpeg, an image rendering library, compile it with a WebAssembly compiler. It's going to produce a sandbox binary. Then if I stick it into an application like Firefox, that libjpeg is isolated to a very specific portion of the address space. So any buffer overflows that happen are also contained. So this is the way sandboxing typically works in these systems. And all of this works great. It's being used in production. Millions of users are affected by this or use this. But there is a cost. SFI isn't perfect. And in fact, it really has some fundamental limitations baked in with respect to how performant, how well it scales, and so on, that affect real applications today. And so for the rest of this talk, what I'm going to do is talk a little bit about the challenges with using something like SFI. Then I'm going to talk about our proposed solution, HFI, which is hardware-assisted fault isolation. And finally, I'm going to talk about how we can use something like HFI in real workloads to secure and speed up isolation. Right? So let's jump right in. Yeah, so the challenges with SFI, the problems it faces, these are really fundamental. And it comes down to which style of SFI you want to go with. There's typically a couple styles. The first one is very simple. It's just insert a bunch of bounce checks. So every time you have a memory operation, throw in a bounce check to make sure that that memory operation lives within that little memory that you've specified. Super simple, very slow. 40 to 100% overhead, plus it's extra prone to specter because there are bounce checks all over the place. The other approach, which is the approach used in practice typically, is you specify that sandbox size is going to be 4 gigs, and then you follow it up with 4 gigs of unmapped guard regions, and then you set things up so that all memory accesses land in that space. So anything that goes outside that 4 GB will hit the guard region and trap, and that's how you get security. The downside of this approach, well, the upside of this approach is it's fast, there's no overheads. The downside is this is a trick that works exclusively for this around 4 gig sandbox size. It doesn't work for 64-bit sandboxes with more memory. And what's more, it's wasting a bunch of virtual memory with this guard region, which puts a cap on the total number of sandboxes you can have in your process because you wasted a whole bunch of virtual space. And additionally, this at its core is again an MMU, a TLB-based approach with page permissions, meaning any interactions like resizing the sandbox is now slow again because of, you need system calls which change TLBs, which have TLB shootdowns, and a whole bunch of associated costs. And finally, it turns out this is vulnerable to Spectre too, so there's no magic about it. And so the question I hope you have at this point is, can hardware help? Like ASPLOS, we certainly hope it can. So if we had this hardware, what would we want? Well, we actually really want to balance three things simultaneously. One is we want this hardware to have a simple microarchitecture, easy to implement across a range of CPUs, across different architectures, x86, ARM, so on. We want something that requires very minimal OS kernel support because we have a whole bunch of operating systems. Some of them are closed source, we don't know all the details. The more kernel support we need, the harder it becomes to support. And finally, we want this hardware to provide very flexible primitives. We have existing compiler toolchains today, and some which even do isolation like WebAssembly. We want those toolchains to be able to pick up these primitives easily. And so this brings me to HFI, which is hardware-assisted fault isolation. And HFI at its core is a user space ISA extension, which allows application to express data and control flow restrictions. And as you might expect, we've designed HFI so that it really requires little to no operating system changes and only requires simple CPU changes. And HFI is built on a couple of key abstractions, the first one being regions. Regions are just portions of your address space. You can specify it with a base and a bound, that is to say a start address and a size. And you also get to specify permissions for each region. The second primitive we have is a couple of instructions called HFI enter and HFI exit. And the intuition looks like this. An application can isolate buggy code by specifying regions and their associated permissions, calling HFI enter, which enables all of the region's restrictions, execute the potentially buggy code that it wants isolated to these regions, and then calling HFI exit to disable the protections. So hopefully all of this is relatively straightforward. And the benefits of this sort of approach that we're trying to get across is that by setting things up in this way, by describing all of this in just simple regions, in terms of regions, we get to simplify and improve a bunch of common operations. Things like memory isolation tends to be cheap if you can figure out a simple hardware implementation. None of this involves the kernel, for example. The sandbox setup teardown is cheap because it's all just specifying regions. Context switch overhead is cheap. System call interposition, which I won't get to in the talk, but we go into the detail of the paper, is also something that we know how to do efficiently. And we can also scale. We also remove the limitations of scaling because we don't rely on guard pages. We don't worry about storing the state of multiple sandboxes. We can also ensure things like Spectre safety. So this is what these are all the benefits this sort of abstraction gives us. So let's think through about how actually implementing these regions. And naively, implementing regions is actually kind of hard. Because if you do the most naive thing of just going to your data path, adding a bunch of bounce checks for every memory access, this is extremely difficult. Because you have this challenge. You cannot introduce new pipeline stages. That slows down the world. No one likes that. You also cannot introduce a bunch of complex circuits into the data path. I think someone used this analogy, which I find interesting, which is the data pipeline is the Manhattan of real estate. You really can't get a lot of real estate there. So the insight we had to actually make all of this practical is we want specialized regions. Regions with specific restrictions and specific use cases. And so we've defined a few different regions. The first one is an explicit data region. And this is actually a region you can use for relative addressing. The idea being you can specify the region you want to access, specify an index, that index is bounce checked. This region also comes with a couple of extra restrictions, which don't really matter in practice, but what it lets us do is build all of this support with a single 32-bit comparator, which is a very simple hardware implementation. And we also have a couple of other region types. This is called the implicit data regions. And what we're doing is checking that each memory operation has a certain prefix. So we can set up a rule like, if you have the prefix 0x1234, you get to read but not write to this region. And there's a very similar one for code regions which which checks the prefix of the program counter as well. And so all of this might look simple, but it took a lot of iterations to actually get to this because and this is the assertion I'm going to make, this is the balance you need to make sure this is easy to implement in hardware, easy to adopt, and easy to use in real applications. And there are a bunch more details which I can't, I should specify. The implicit regions are implementable easily because it's just masking. It's just and and or operations, which are relatively cheap. And there's a few more details I wish I could get to, but it's in the paper, it's there, you can ask me questions about it in case you're curious. But it's things like how do you grow regions efficiently, how do you avoid fences, how do you deal with system calls, signals, and so on. And if you kind of put all of HFI's primitives together, which is all of these new region types and things like system call interception, you actually get what you wanted, which is the ability to have hardware support for WebAssembly isolation, but also native code isolation, which is, you just isolate an unmodified binary someone gives you. So to see if all this actually works in practice, we simulated and emulated HFI with a bunch of techniques, and we actually measured the performance and the security that we would get if we had something like HFI. So for example, we modified a WebAssembly engine and ran the spec benchmarks. And when we did this and compared the performance, we see that a WebAssembly engine that uses HFI instead of bounce checks and guard pages is faster. And compared to bounce checks, it's a lot faster, as you might imagine. Compared to guard pages, the speed up is smaller because guard pages don't have that much overhead. But this also has a couple of the HFI version has a couple of advantages. It is spectre resistant, and it does not impose the scaling limits that virtual memory-based techniques have. So it's performance boost with a bunch of additional speed ups. And it turns out in some other workloads, we even see even higher speed ups. So the speed ups do seem to be workload dependent sometimes. But where HFI really shines is in some of its scaling benchmarks. So this is common operations that happen in an edge platform, which have to spin up and destroy a bunch of sandboxes all at once. So when we instantiate a whole bunch of WebAssembly sandboxes with guard pages, because of the guard page wastage, you get only about 16K per process, whereas HFI kills the guard pages, you get to scale as much as you can, put as many sandboxes as you can fit. And the same thing affects cleanup as well. When you're cleaning up sandboxes with guard pages, you have to do them one at a time because of all the gaps. Whereas with HFI, they're all put together, so you can actually batch the cleaning, which again speeds things up and gives you a lot of economics of scale. And there's more eval in the paper, but let me just quickly summarize since I'm nearly out of time, which is HFI is a user space extension, ISA extension for in-process isolation. It's designed to be easy to adopt, not just by WebAssembly engines and native code, but across operating systems and different CPUs. The key abstractions are regions and a few extra instructions, and all of this is designed to be a very light touch change to CPUs. So thank you for your attention, and I'm happy to take questions.